we start a new topic, Part C, Smoothness Rule and Fibonacci Numbers. Part C.1, Smoothness Rule. So this is a pretty abstract rule so that we can use to just do something that we just did to get a general solution for the binary bits problem. Remember, we used the mathematical induction to prove it's correct. But this one, with smoothness rule, we can get the general result from the special result directly. So that's pretty nice. Yeah. So let's look at this rule. Yeah. All right. Here. So look at, suppose we just, get our problem using this recurrence relation to represent it. Okay? Yeah, to make it as simple as possible. Now, what do we have? We have a special case. The special case is when n is power of 2, we have this formula. The next, we need to go to the general case. But for the general case, we need to do some work, right? Yeah. In our previous video, actually, we did a lot of work. So you can think about the mathematical induction, how much work we did using mathematical induction. A lot of work, right? Yeah. Now we want to take a shortcut. Shortcut, okay? Is there some existing theorem? When we apply it, we can get the general result directly. So that's the plan we will do it right here, okay? Existing theorem. So let me introduce that theorem first. Concept, smoothness rule. Smoothness rule. Yeah. So that's the theorem we will use. Yeah. The reference is in Appendix B. The situation, I just described the situation. We need a general result. Regarding the situation, I just described it. Okay, yeah. So I do not repeat it another time. Yeah. So let us look at this smoothness rule. So what's that? What do you mean smoothness rule? Right? Yeah. A lot of explanation here. Yeah. It's pretty abstract. Yeah. Not easy to master it. Yeah. So we need to do some practice to get used to it. Yeah. All right. So here. Let T of n be an eventually non-decreasing function and f of n be a smooth function. Two concepts. The first one, eventually non-decreasing function. I think from the name, you can understand the meaning, right? You understand non-decreasing function. No, non-decreasing. Non-decreasing. Eh? You can only increase the function value or going flat. Flat is okay, but non-decreasing. Right? Yeah. Now, eventually, not eventually. So at the beginning, you do not have to have that. Okay, beginning, your function can go up, go down, up and down, no problem. But you need to have some starting point. After that, you're not allowed to go down. Okay, yeah, you have to go up or going flat. Yeah. All right. Then, if T of n belongs to big theta of f of n, Yeah, but here f of n is a smooth function. What is the smooth function? Next slide, I describe it. Yeah. Because it's not easy to describe it in just a few sentences. Yeah. All right. For value of n that are power of b, where b greater or equal to 2, then here you can see b greater or equal to 2 for power of b. How about this? Okay, b equals 2. Power of b greater or equal to 2. So you can see our binary bits problem fits this model pattern exactly. Okay? Yeah. All right. Conclusion. So then T of n belongs to theta of f of a. This time power of b condition is removed. Right? Yeah. If condition, there is a power of b condition. But for the conclusion, there is no power of b requirement, right? The reason is f of n is a smooth function. F of n is a smooth function. Here, the meaning of the smooth function is different from the one you learn in calculus. In calculus, you have a smooth function, right? Yeah. So let me recall a little bit. Calculus. You have a smooth function concept, right? Do you know what's the meaning of smooth function in calculus? Right? Smooth function, the meaning calculus. Yeah. Its derivative. The function, its derivative is continuous, right? Yeah. In calculus, when we say f of n, yeah, we use f of x, right? Yeah, because we use that continuous variable. Then we can take a derivative. Okay, smooth function means its derivative, f prime of x, right? F prime of x, that's the derivative. Yeah. Its derivative is continuous. When you look at the graph of the function, it's pretty smooth. Derivative continuous, pretty smooth. You're not allowed to have, the wedge thing like that. This tells us derivative is not continuous. Yeah. So derivative here, there is a jump. Okay? So that jump means not continuous. So that's the calculus smooth function. Here, completely different. Do not get confused. Yeah. Many of you get confused, smooth function. Yeah. All right, yeah. Let's, yeah, sorry. Sorry. Yeah, in the previous slide, yeah, I didn't show you, right, the condition, okay? So then the conclusion, yeah. All right. Okay, so let's have some more understanding. Yeah. First, eventually non-decreasing function. So that's pretty straightforward. Okay, yeah. We need some non-negative integer f0. So that corresponds to eventually. Yeah. So what do you mean eventually? So you need to get some special point n0. After that, that function satisfies that non-decreasing condition. Okay, yeah. So that is the easy part. Okay, example, the floor function of log base 2 of n eventually non-decreasing. Yeah, no problem. No. But that one going flat a little bit, right? Yeah, there is, because floor function in some interval, the function value is flat. Okay, yeah, flat. Yeah. Then smooth functions. Yeah. Let f of n be a non-negative function defined on a set of natural numbers, f of n. So let's look at the main condition part. F of n is called smooth if it is eventually non-decreasing and f of 2n belongs to big theta of f of n. This is the key condition. Key condition. Yeah. Other part, pretty simple. Yeah. But this one is the key condition. When I ask you to check if a given function is smooth or not, you check this condition. Okay? Check this condition. If it is satisfied, then smooth function. Yeah. All right, so here, let's look at our simple example. In our example, we want to show this function is smooth in our algorithm context, not in the calculus context. Okay? Not in the calculus context. Yeah. All right, so let's look at f of 2n. Yeah, this is f of 2n. That equals 1 plus floor function log base 2 of n is this new representation belongs to big theta of that old f of n function? Yes. Yes. We can easily see it because this constant 1, we can easily use inequality, replace it by just the same function. How about that? Just same function. Yeah. All right. So anyway, you can also use the limit way to see it's in the big theta of n, right? Yeah, because big theta, as I told you before, big theta, the limit way is a good way to prove it. Prove a function is in that big theta. Okay, limit way. Yeah. Yeah. All right. So now you can see if you can apply the smoothness rule on the similar situation we have in that binary bits problem. Then we do not need to use mathematical induction. We can get a conclusion immediately. So we save a lot of work. Okay? Yeah. Although as a practice, it's a good practice for the mathematical induction. Yeah. Yeah. As a practice, you need to do it. Yeah. But we have this shortcut. Very nice shortcut. Yeah. All right, so let me start our first video C.1 right here.